Okay, great. So what have we been looking into? So on Monday, we talked about clock arithmetic. So if you look at the clock, as the minute hand goes around, or as the hour hand goes around, it goes back to where it started. And well, then you end up back where you started. And sometimes in real world examples, you end up just not quite exactly where you started, but somewhere very familiar. And so we can invent a type of mathematics to quantify exactly what we mean by that. And that's what we did with clock arithmetic. So I brought in the ball, we had the QQ penguin walking along it, and you realize that if you're counting steps along a circle, well, eventually, if you count enough steps, you'll get back to 0. Which is, of course, quite different from what happens normally when you're counting steps, at least in an infinitely flat plane, because then you keep on counting steps, you keep on getting further and further away, you don't ever end up getting back to your starting point. So today we're going to focus in and spend a lot more time on exploring what addition, subtraction, as well as multiplication mean in this context. So we've invented a new set of numbers, and now we are asking ourselves, well, what does math look like in this new set of numbers? So we're going to do arithmetic mod 5, because 5 is a small number, which makes life a little bit easier. So what we're going to do is we're going to construct a circular line with 5 positions. So let's draw a circle, and let's say that's 1 position. Let's see, 2, 3, 4, 5. Okay, we have 5 positions, and now in theory we could label these with any names we wanted to. So if we wanted to, we could call these things like triangle, square, star, circle, squiggly, whatever you want. So one thing that you should keep in mind is we are going to use ordinary labels because we're all used to numbers 0, 1, 2, 3, and 4. But you can use whatever labels you want, and the label isn't the object. So what we're referring to these points around the circle, and we can label them whatever we want, including, say, 0, 1, 2, 3, 4. But I drew out these symbols just to really drive home the point that these aren't what you normally think of as counting numbers. And we'll see some of the differences between what we've labeled as 0, 1, 2, 3, 4 and what we normally label as 0, 1, 2, 3, 4 in lecture today. And so try not to be confused by that. We're using the same labels, but they don't mean exactly the same thing. But of course, there is some relationship between them, which is why we do label them this way. And so if we're counting steps along the circle, oh, I don't know why I have an arrow there. So let's start by asking a simple question. So let me redraw out my circle. So hopefully that's pretty obvious. 0, 1, 2, 3, 4. If I walk n steps around the circle, where do I end up? So this should hopefully be fairly easy question. So if I walk 4 steps around the circle, starting from the top, and then I walk 4 steps, at what position do I end up? So remember, I am starting right here-ish, and then walking 4 steps. So I start at 0, importantly. Oh, sorry, I start at 0, and then I walk. 1 step is going from 0 to 1, and then another step is going from 1 to 2. Okay, and so that's going to look something like 0. Oh, come on. Okay, so yes, so I'm starting at 0, and then I walk a couple steps. So 0, that's 1 step, that's 2 steps, that's 3 steps, that's 4 steps. So after walking 4 steps, I end up at 4. And let's zero that out. So what happens if I walk 5 steps? Where do I end up? Okay, yeah, so it's pretty obvious, right? I just take 1 more step, and then I end up back at 0. So that goes to 0. Wasn't very good at drawing that. Right, and this is the same way where if you're starting at 12 o'clock, and then you wait 12 hours, well, you end up still at 12 o'clock. So it is AM or PM in the case of time. Okay, what about 8? If I walk 8 steps around the circle, where do I end up? Well, I mean, we already know what it is to walk 5 steps. So if you walk 5 steps, you end up back at 0. So if you walk another 3 steps, well, then you end up back at 3. And I'll just have you notice that that is 5 steps plus 3 steps. And you know 5 steps gets you to 0. So this is the same as 0 steps plus 3 steps, which is of course the same as 3 steps. Okay, let's do one more of these. Hopefully you guys are getting in hand now. So if I go 11 steps, starting from 0, where do I end up? So of course you can count around, but you can also take advantage of the fact that you already know what it is to go 5 steps or 8 steps, or well, maybe you know how many it is to go 11 steps. Yeah, and so this is just going to be going 5 steps, and then 5 steps, and then 1 step, which is of course the same as going just 1 step, because 5 goes around a complete circle. And I'm going to write it out slightly differently, because this is also the same as saying 5 times 2 plus 1, and which of course goes to just 1. And I write it out this way, which you guys have seen me write out that kind of notation before, because really what you're doing is, there is some general rule, right? So does anyone want to tell me what the general rule appears to be? So the hint that I'm giving is, of course, that writing things out in list notation ought to be very evocative. When else do we write things out that way? You can either answer in chat or shout at me. Yeah, it's just the remainder. Yep. So 5 means goes back to 0, and you do this over and over again, which means you're basically dividing by 5 and then taking to see whatever is left over is how many steps along that you've gone. So the answer is, of course, it's the remainder. Remainder of n divided by 5, where n is whatever number of steps you're taking. So now that you know that, this should be easy. So how about 45? Where does that go? Okay, yep. So 45 is divisible by 5, and so that clearly goes to 0. What about 502? So now we're getting the numbers that are way too big for you to actually count around. But now that you have a general rule and we have all these other tools, hopefully that shouldn't be too difficult. Because somehow, originally you started out with this basic idea. You had this repetition over and over again. And now we're as mathematicians, we're coming up with ways of figuring out what the answer is faster without actually having to draw 502 like steps along the circle. And so this is going to end up going to 2. Oh, I switched colors. Didn't even notice I was doing that. Oh well. What about this? What is this number? 21,938,193. So where does this go? Oh, let me zero that out. And you'll notice that one of the reasons I chose to do mod 5 instead of a mod some other number is because it's really easy to find the remainder of mod 5, right? Because you only have to look in the 1th digit for this. But yeah, so if you divide this, the remainder is just going to be 3. Someone suggested just take the last digit, but you have to be a little bit careful about that, because what if I had, I don't even know what this number is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 349 quadrillion, 592 trillion, 20 billion, 124 million, 854, 8,826. Yeah, so well, you only look at the last digit and divide that by 5, because of course 10 is divisible by 5, so any multiple of 10 is also divisible by 5. And so this goes to just 1. Okay, so far this seems pretty straightforward, right? You just take the divide and then take the remainder, and then you're, well, done. So now that we've figured out this whole idea of like going around in circles, which isn't super complicated an idea, well, as mathematicians, we want quicker ways, easier ways of writing this down unambiguously. So what we're going to do is let's talk a little bit about notation. Since I will write this down a couple of different ways, and you may see this written down a couple of different ways, and I want you to recognize it when it happens. So there are several different notations for remainder that we might use in this class, and I will use them at different points, and so you should know what they are. So 6 remainder 5 is equal to 1. So that's one way of saying it. So 6 divided by 5, what's the remainder, is 1. Another thing I might write is 6 mod 5 is equal to 1 for the modulus, which is the remainder after division. And sometimes you'll also see this sideways division sign, this sort of slanted division sign, to be equal to mean remainder. I will try not to use that notation as often, but you should know it because it is a notation that you'll commonly see, especially if you do any sort of programming. So if you do programming, this is a very common division, a very common notation for that. It's this percent sign thing. Or no, sorry, yeah. So notice that this is 6 is equal to 5 times 1 plus 1. And so 6 divided by 5 is equal to 1, remainder 1. Okay. The other thing I really want to emphasize is that I'm using these ordinary symbols, right? I'm using these symbols that we also use for numbers. So I draw out some circly squiggle, and then I say that's the number 0. I draw out some like squiggle that intersects itself, we say that's number 8 or whatever. But these are not the same as normal numbers. And so we're not going to use the same equal sign symbol. It's usually conventional to use a triple equal sign to refer to things that are the same under a modular arithmetic. So I might say something like 6 is equivalent to 1 mod 5, or 12 is equivalent to 2 mod 5. And the reason for this is just, I might mess this up. So if I mess this up, just call me out on it. But the reason for this is just, it's sometimes useful to write down a slightly different notation because we're not talking about the same numbers. They look almost like the numbers we all know and love, or maybe not love, but all know at least, but they behave differently in certain ways. We haven't really seen how they behave differently yet, other than that like whenever 5 is equal to 0. But there are several other ways, especially once we get to powers and division, where these things behave quite differently. Okay, where was I? Okay, the other thing I want to emphasize is these are just labels. So remember, there are only 5 numbers in mod 5 arithmetic. So we happen to have labeled them. So there are only 5 numbers. We happen to have labeled them 0, 1, 2, 3, 4. But just like with the ordinary numbers, you can sometimes have different labels for the same number. 2 over 2 is another label for the number of 1, right? If you're talking about fractions. But, well, what's another label for the number 0 in mod 5 arithmetic? We've been using this consistently. So, like, what is equivalent to 0 steps? Yes, 5 steps, right? So that's the whole point of mod 5 arithmetic. So we might say that we could also label this 5. You could also, if you want to, you could also label it 10. And somehow these are all equivalent labels. So that's also 7, also equivalent to 12, equivalent to 8, equivalent to 9, and so on. But yeah, so, and you don't have to use just these labels. You could also label them squiggle, square, triangle, pentagon, whatever. But those aren't as useful in some ways because somehow these labels correspond to how many steps you're taking if you're just counting upward using normal counting. And so that's the reason we use these labels for these numbers, even though they're not the same numbers. There's another way of thinking about how we're doing this labeling, which is you can sort of imagine taking a real number line. So normally you have your real number line, which has like, let's say starts 0, 1, 2, 3, etc. And we're basically curving it around. So we're basically starting here and then we're doing over and over and over again. You're basically wrapping the real number line around it. And that gives you this other set of labels. Any questions about that? Okay, great. Okay, so now we have counting down. Well, what's the next step after counting? Mathematicians invent counting, and then what do we invent after we invent counting? Faster counting. Yes, faster counting. That is the correct answer. What's the next level of counting? Oh, someone mentioned adding. Yes. So adding is a way of doing faster counting. And so that is the next step there. Yes, then later on we'll get to multiplication. And along the way, we might invent subtraction as well, but we'll see whether or not that's what that really means. So how do we do addition mod 5? Well, addition is just repeated counting, right? And so you could do this just by doing like saying 5 plus 5. Well, that's you take 5 steps and you take another 5 steps. And there's a general rule for mod 5, which is you just add the numbers together and then you find the modulus, the remainder after dividing by 5. So that's relatively straightforward. So if we have, again, we have our circle here, 0, 1, 2, 3, 4. You might have things like, well, what's 2 plus 4 in mod 5? Well, you take your 2 steps, 1, 2, and you then take another 4 steps, 1, 2, 3, 4. You notice that's the same taking 2 steps and then 4 steps. We already all know is the same as taking 6 steps. But we know that 6 steps is equal to 1 step, right? And so this is equivalent to 1 mod 5. And of course, you can see this because 2 plus 4 is equal to 6. And 6 divided by 5 is equal to 1, remainder 1. And you can also get other things like, see, 3 plus 3 is also equivalent to 1 mod 5. And as you all hopefully all know, 3 plus 3 is also equal to 6. So let's have you all try it out. And zero that. So find the value of x. And we're working in mod 5 arithmetic. So what's 4 plus 3? Okay, yeah. So this is equivalent to 7 mod 5, which is equivalent to 2 mod 5. Okay, what about 1 plus 4? Okay, yeah, and this should just be equivalent to 5 mod 5, which is of course equivalent to 0 mod 5. And I think I have 2 other ones. So let's go through these fairly quickly since you all seem to know what's up. So this one should be fairly straightforward. What's 0 plus 2 equal to? What's 0 plus anything equal to, really? Yeah, so it's just equal to 2. So I guess I'll write that down, but 2 mod 5. And let's give one last one. So what would be 4 plus 14? What's that equivalent to? Okay, yeah, so this is equivalent to 18 mod 5, which of course is equivalent to 3 mod 5. Okay, easy enough, right? So add them together, divide by 5, find the remainder. Everyone's happy. So that's addition. But when we went into this a little bit at the end of lecture last time, well, what about subtraction? Can we do subtraction? What does subtraction mean when you're in this sort of weird circular number line? Well, one thing you might do is you might be like, well, I can construct an addition table. And you should verify that this is an addition table, but you all should be able to construct this now. And then the question is, well, we know that subtraction is the opposite of addition. So there are several different equivalent ways of thinking about this. One way is that if you happen to have a number, let's say, if you know 3 plus 4 is equivalent to 2 mod 5, well, then that means that you want it to be the reverse, right? So you want 2 minus 4 to be equivalent to 3 mod 5. You're just taking the reverse of it, right? And so you're just being like, well, we know that 3 plus 4 is equal to 2, which means that 2 minus 4 ought to be equal to 3. Now, this probably looks a little odd, right? Why is 2 minus 4 equal to 3? Well, and for that, let's think about the other way of understanding subtraction. So remember, when we were on the ordinary number line, well, addition was moving things to the right, and subtraction was moving things to the left. Actually, sorry, I have this backwards for you, but yeah, mirror in your head. And so what happens when we're doing it on a circle? Oh, gave away the punchline. So we have 0, 1, 2, 3, 4. Well, what is 2 minus 4? Well, what we're doing is that means we're moving forward 2. So we're moving clockwise 2, but then minus 4. Well, another way of thinking about that is we go the other direction 4 steps. So if you go the other direction 4 steps, well, what is that? Well, you go backwards 1, 2, 3, 4. And one of the things that you'll notice, right, is that whenever when you're going backwards, when you're going counterclockwise along the circle, you still always end up at one of the numbers you already have. And so for this reason, we don't need negative numbers, because no matter what you subtract, you're still somewhere on that circle, because that's the whole point of a circle. The issue we had with the number line originally was that if you just had the positive number line, 0, 1, 2, 3, what happens when you move to the left? But when everything's a circle, you don't have that issue, because moving to the left still stays on that circle. In the same way, like getting bigger, well, you don't need more numbers to get bigger either, and so you don't need more numbers to get smaller. Does that make sense? Okay. So we don't really need negative numbers, but it's still sometimes useful to have some idea of negative numbers, right? So negative 5 plus 5 in ordinary arithmetic is always equal to 0, right? Negative 123 plus 123 in ordinary arithmetic is always equal to 0. So somehow negative numbers serve another purpose as well. Like they allow us to label things that are the opposite of the ordinary numbers. And so if you add them together, you end up, going back to your starting point, going back to 0. And so that's something that we might want in the case. And the other thing is that negative numbers allow you to just use addition. You didn't have to have those two different operations. You just add the negative of something. And so the idea of a negative number is still sort of a good idea, right? Because it allows us to do addition instead of doing just subtraction. And so let's notice something, which is, let's not use green. So notice that 0 minus 3. Well, let's draw this out. So 0, 1, 0, 1, 2, 3, 4. Well, what's 0 minus 3? Well, that's going 1, 2, 3. That's equal to 2, right? Oh, sorry, equivalent to 2. I'm not going to bother writing the mod 5 for now, but just know that there ought to be a mod 5 there just to tell you what we're taking things mod. And let's see, what's 1 minus 3? Well, 1 minus 3 is you start at one further along, you go back, and so that's equivalent to 3. 2 minus 3 is equivalent to 4. 3 minus 3, well, that one's easy, so that's equivalent to 0. And 4 minus 3 is equivalent to 1. Right? And I'm going to claim that there is an additive inverse, which is for 3, which is just 2. So you notice that at the same time, 0 plus 2 is equivalent to 2. 1 plus 2 is equivalent to 3. 2 plus 2 is equivalent to 4. And 3 plus 2 is equivalent to 0. And 4 plus 2 is equivalent to 1. So what's the conclusion? Well, adding 2 is the same as subtracting 3. Right, and so clearly what this means is that instead of, we don't actually need subtraction in some ways, right? You can just add the appropriate number, and you don't even need to invent a new set of numbers for it. So back in the day, we had to invent negative numbers in order to add a number and get something equivalent to subtraction. But right now, we don't. Let's see, so there's no negatives. Well, yeah, so it seems like we don't really need negatives, right? But sort of the point is, it might still make sense to talk about taking negatives of things, and that's what we're going to do now. So let's talk a little bit about labeling. So, well, we didn't need the number 6, right? Because we already had the label of 1, and moving 6 steps is the same as moving 1 step. But it was still useful to have both labels, right? Because that meant that we could easily translate things between one thing to another. And so we can add even more labels to make it easy to encode additive inverses. So something like -4 is equivalent to 1 mod 5. So what do we mean by that? What I mean is that subtracting by 4 is the same as adding 1. And if you think about a circle, that sort of makes sense, right? If you go 4/5 of the way around one direction, that's the same as going 1/5 of the way the other direction. And this is generally true. And even though we don't need to invent negative numbers, it's still useful to have this idea of what it would mean to have negative numbers, even though those numbers are the same as our positive numbers. There isn't really any idea of positive and negative when everything's just around in the circle, right? Because on the real number line, well, positive means that you're on the right side, and negative means you're on the left side. And so there is no right and left on the circle, and so you don't have that sort of idea to begin with. But they're still useful labels, so let's go ahead and label some of that. So let's see. I really should have just made a bunch of copies of the circle because I'm drawing it many times, and I think I'm getting worse at drawing the circle as I get more impatient with drawing it. So 0, 1, 2, 3, 4. Well, we knew that this was equivalent to 5, and this was equivalent to 6, and this was equivalent to 7, and this was equivalent to 8, and this was equivalent to 9, etc. But we can also say something like, well, this is also equivalent to -5, right? So if you go left, if you go counterclockwise 5 steps, you also end up back at the beginning. This 1, well, that's also equivalent to -4, right? Because if you go counterclockwise 4 steps, that's the same as going forward 1 step. You end up at the same place. And this is also equivalent to -3, and this is equivalent to -2. This is equivalent to -1. Right, and so we can keep on going. So you can also get a label -10, and then you can also label this like -505 or whatever. And those are all valid labels. And so remember, like, this is because when we take the real line, we're basically wrapping it around many, many times. Well, you can wrap it around in both directions and just have it looping around infinitely. And that's another way of creating a bunch of labels for this mod 5 number circle. Let's see, when was clock arithmetic invented? That is a very good question, and I will be asking that question of you in the second half of lecture, so I'm not going to answer that right now. But yes, that's a very, very good question. There's no negatives, yes, okay, yep. And so this is why I wanted to make it clear that, like, if you remember back when we were talking about decimals, I asked you, is 0.999 repeating the same as 1? And the answer to that was, well, it depends on how you define repeating decimals. But if they are the same, it's because you're just putting different labels on the same number. And in the same way that 3/1 is the same, it's a fraction, but it's the same number as 3. So you can put all these different labels on things. 2 plus 2, you could even think of as a label for 4. And in the case of clock arithmetic, negative numbers are just a different relabeling of your positive numbers. Okay, so now that we have that, oh, wait, what just happened? No. I hit the wrong button. Oh, okay. I don't even know what number I hit. Oh, rehearsal button. Okay, anyway. So let's now go back to subtraction. So obviously you can do this by just figuring out how many times around the circle you're going to the left or to the right, or finding the equivalent numbers. But let's actually come up with a way of basically an algorithm for doing it. Yeah, so remember when we invented the normal number line, we already invented the normal number line. And so even though that's not what we're inventing here, we can still use those ideas. And so a shortcut for modular arithmetic is to do things on the normal number line, right? And then you wrap the normal number line around your circle and you figure out what place you are. And so that's a shortcut for doing modular arithmetic if you already know how to do ordinary addition and subtraction. So now, if you guys hadn't spent 12 years or however many of your years of your life learning the ordinary addition, subtraction, multiplication, and division, then what I'm going to tell you here doesn't make any sense. Because what's this idea of a number 6? Like, you can only count up to 4, right? But or maybe count up to 5, depending on how you do your counting. But the point is, though, that because we already have this other sense of numbers, we can use that to help us with this and understand it better. Even though you could, in theory, invent this clock arithmetic without having invented ordinary arithmetic. That is completely possible, though that is not how human minds work, at least. Let's see. So a shortcut is to do things on the normal number line and convert. So 1 minus 4, well, that's equivalent to minus 3 mod 5. And we know that minus 3 is equivalent to 2 mod 5. And so that means that, of course, 1 minus 4 is equivalent to 2 mod 5. And you'll notice that that's because minus 3 plus 5 is equal to 2. Right? Because anytime you take a step of 5, that's equivalent to doing nothing. Another way to think about it is on your, I forget if it was your quiz this week or last time, but on one of your quizzes, I think it's this quiz, I tell you that the way of finding different ways of writing a combination is to add 0 to things, right? And basically adding 5, when we're dealing with clock arithmetic, adding 5 is the same as adding 0. So another algorithm to convert a negative modular number to a canonical representation 0, 1, 2, 3, 4 is 2 steps. The first is just you add a multiple of 5 that's big enough to make it positive. And then you divide by 5 and take the remainder. Because we haven't really talked that much about dividing negative numbers and taking remainders. That's basically what you're doing. But you can do that by just like adding a multiple of 5 big enough to make it positive, and then you just use the positive algorithm. Let's have you try this out. So, you guys know the drill now? Oh, there's a good question. If we don't need negative numbers, then why do we still use them? Well, the answer is you don't have to. You don't have to use them. But we already know what negative numbers are because we already learned ordinary arithmetic. And so because we already know that, sometimes it's useful to use that tool. If you wanted to, you could not use negative numbers at all and just use these 5 numbers and use the addition table, figure out the subtraction table, and it would all still work out. But I'm taking a shortcut. I'm basically cheating because we already know all the stuff about ordinary arithmetic. Okay, so let me zero out the chat. What is 1 minus 3? Okay, so, well, let's see what does this equal to? Well, one way of doing it is you just do the subtraction of the ordinary arithmetic first. And so that's equivalent to saying this is equivalent to minus 2 mod 5, which is equivalent to minus 2 plus 5, which is equivalent to 3, right? Or you could also write it a different way. So notice that there are often different ways of solving this. So another way is, well, you know that minus 3 is equivalent to 2. We already figured that out. So, or you could say that 1 minus 3 is equivalent to 1 plus 2, which is equal to 3. Let's do another one. What's 4 minus 3? So what was the algorithm? Do it in ordinary numbers first and then convert. Well, when you do this in ordinary numbers, 4 minus 3 in ordinary integers is just, of course, equal to 1. And And so, well, that's already one of the canonical labels. And so you end up with just one. Let's do something a little bit harder. What's minus just negative 31? What does that equal to mod 5? Okay, so it looks like I wasn't able to trick you all. So that was the goal, but I failed at that. That's all right. So you have to be a little bit careful when you have negative numbers because you need to add a positive number big enough to make it like circle around. So this is equivalent to, well, it's just minus 31. And so you could do minus 31 plus, say, 50. 50 is a multiple of 5, so that ends up giving you 19, which is equivalent to 4. Or if you happen to know the multiples of 5 a little bit better, you might be like, well, that's equivalent to minus 31 plus 35, which is equivalent to 4. Okay, so both are valid ways of doing it. You just need to add a number big enough and then go the other direction. And let's do one. Could you not just do minus? Oh, yes. So someone has a really, really good point. Could you just do minus 30 minus 1? Yes, of course you can. So that's another way of doing it. So this is also equivalent to minus 30 minus 1. Minus 30 you already know is 0 because it's going exact multiple of 5. That's equivalent to minus 1, which is equivalent to 4. Yeah, so there are lots of different ways you can do it because all these numbers are different labels for the same thing. And so you can do your operations in different orders and you will still get the same answer. Or you had better get the same answer. In fact, one good way of checking your answer is to do it a slightly different way and then see if you still get the same thing. And if you don't, well, maybe something went wrong. Okay, and let's do one more of these basic ones. So what's 4 minus 31 equal to? So I'm walking forward 4 steps and then walking backwards around the circle, another 31 steps. Okay, yeah, and so there are a couple different ways of doing this one. So let's start with the very simplest way, which is this is equivalent to minus 27, which is equivalent to minus 27 plus 30, which is equivalent to 3. Another way of doing this, sort of like the way that the commenter suggested a moment ago, is this is also equivalent to minus 1 minus 31, which is equivalent to minus 32, which is equivalent to minus 30 minus 2, which is equivalent to 3. Okay, so there are all sorts of different ways you can transform this thing to make life easier for you. And whatever way you do, you should end up getting the same answer. Yes. Or you could do the previous answer and do 4 plus 4. Yes, that's a very good point. So once you figured one answer out, well, the previous answer, you knew that minus 31 is equivalent to 4. So then 4 minus 31 is equivalent to 4 plus 4, which is equivalent to 8, which is equivalent to 3. Yep. And so there are a ton of different ways of, let me make sure that's, yeah. So there are a ton of different ways of doing this. And you should do whatever makes the most sense to you in your head, because they are all equivalent. So now, what's so special about the number 5? So does anyone want to take a guess as to why I used the number 5? It feels complete. It's prime. So primeness does have an effect eventually, but it actually doesn't do anything for addition and subtraction. Mod 5 arithmetic only has 5 points on a circle. Easy to divide by. Easy to see. Uneven. Okay, these are all very good points. It is easy to work with, and that does help a lot because it means I can do things like give you 400 quadrillion something and then tell you to divide by that, and you can do that relatively quickly. But the real answer I went with 5 is because I have 5 different things that you can vote for on my poll. So I have A, B, C, D, or E, and like, well, if I have more than 5 things to vote for, then I don't have enough letters that my polling thing works for. So, but all your other answers were good as well. So yes, it is a lot better, a lot easier to see multiples, and so that's easy to work with, easy to calculate, yeah, and so yeah, easy to divide by and all of that. Okay, but there are of course other modular arithmetics, and you can do this with a bunch of other numbers. You can do the same thing with any other positive integer. You can do the doesn't have to be 5. So for example, mod 4 arithmetic has, well, 4 numbers, 0, 1, 2, and 3. And those look something like, well, if you draw down a number line, you'll notice that these are different positions. And one very important thing to notice is that this is separate from this number line. So 0, 1, 2, 3, 4. So these are 2 different number circles, but we can do one for a 4, and then what do we get? So 3 plus 3 mod 4. Well, that's equivalent to 6 mod 4, and that's equivalent to 2 mod 4. Right? Because what we're doing is we're walking along. So 1, 2, 3, 4, 1, 2, 3, and you end up at 2. Or you can do things the other way as well. So, since the positions are different, does that mean the steps to get from 0 to 1 would be longer for mod 4 than mod 5? So you're thinking a bit too geometrically. We haven't invented any number to measure like how long things are in between. So yes, when I'm drawing it out in the circle, because you see that and you have some sense of like what you're measuring, in that case, yes. But in reality, these circles are just things we're drawing. And so somehow would be longer for, we don't know how to answer the question. This question doesn't make any sense. I don't mean that in any sort of mean way. It's just that we haven't invented what it means for something to be long. So remember how much work we had to do to invent measuring distances? That's basically what we're running into here. We haven't invented measuring distances in mod 4 or mod 5 yet. And so there's no way of comparing. Is there a limit for how many numbers you can have in a circle? That's a really good question. In fact, I'm going to ask you guys that question. So let's say that A is yes and B is no. So do you guys think there's a limit to those? I think that's the first time I've asked one of your questions as a poll. So is there any limit? Do you think there is? Yes or no? Okay, yeah. So the answer to that is no. No limit. Because of course, if you think about it, you can, so long as you have little itsy bitsy divisions, you can keep on going, right? So you can make as small of a division as you want. Now, this doesn't work in the physical world. If I have a pizza and I divide it into a gazillion pieces, well, I mean, you're probably running out of atoms at some point. But in mathematics, you don't have those issues. And so yes, you can divide it up into a gazillion pieces and then keep on walking along. It might take a really long time to get around. And there's some sense in which you might think of that as something closer to a flat line. So remember how when I was talking about just walking along in the room, and this looks pretty flat. The Earth looks pretty flat because it takes so many steps to walk around it. And so somehow if you're dealing with some modular arithmetic that is really, with a really big mod number, really big number, but it somehow looks a bit flatter since you have to take a lot more steps before you circle back around. And let's do another one. So I had this one prepared. So 1 minus 3 mod 4. Well, that's equivalent to 2 minus 2 mod 4. Because what you're doing is you're going around 1 and then back 1, 2, 3. So that's so this is also equivalent to 2 mod 4. And let's have you guys play with this. Let's zero out the chat. So find the value of x. Let's start with this one. Okay, yeah, so, well, this is equivalent to 4 mod 4, which is just equivalent to 0, of course. Well, let's do another one. What about 2 minus 3? And of course, hopefully you guys all read that this is mod 4, because that is something that you have to be a little bit careful about, being ambiguous, because that's what you're actually dividing by. And so this is equivalent to minus 1 mod 4, which is equivalent to 3 mod 4. Okay, what about 1 minus 20? So I take 1 step forward, and I take minus 20 steps, or sorry, then I take 20 steps backwards. Okay, and you'll notice, one thing that you might notice about the number 20 is that it's a multiple of 4. And so this is equivalent to saying 1 minus 0 mod 4, because 20 is a multiple of 4, and so that's equivalent to 1 mod 4. Okay, let's do another one. What about this one? Take a moment to think about it. So someone asked me a little bit ago, like, does it mean that you have bigger steps when you're taking mod 4 or mod 5? And I gave some answer about how like that isn't something we figured out yet. And so what do you guys think is the answer for this one? Okay. Yeah, so there's a question in chat. Can you add from different mod, or is there no answer? Yeah, so this was a trick question. There's no answer. You can't add because they're not the same kinds of numbers. Like, they're completely different number circles, and you can't add them together because they're just different types of numbers. So like, we've labeled them with the same kinds of labels, but they really don't mean the same thing. Like a 4 in mod 4 arithmetic and a 4 in mod 5 arithmetic don't mean the same thing at all. And so for that reason, there is no answer to this. And A, you can't add numbers from different systems. Numbers from different systems. Or at least we haven't defined how to do it. And this particular thing, like, is not something people do. Sometimes, in general, you sometimes can add numbers from different systems, but you have to be really careful about how you do it. And in this particular case, there isn't really a way to add numbers from mod 4 and mod 5, or from any 2 different mods. So like, if you ever see me ask this kind of question, it is a trick question, and you cannot do it. Okay, and with that, I think that is a good halfway point. So let's go ahead and take a 10-minute break and be back at 10:11. And if you have any questions in the meantime, you can ask me, or otherwise I'll just be milling about. So see you after the break.